Now let's change gears a little bit and talk about sample proportions. We use sample proportions to estimate population proportions. For instance, maybe you're interested in knowing the proportion of students who text during class. In order to really nail down the exact proportion of students who text during class, you'd have to round up all of the students who take, people who take classes and get them to give you an honest answer, yes or no. Do they text during class? Of course, we could be talking about tens of thousands, millions, billions, trillions of students. So in order to estimate this true proportion, like we've been doing all along, we settle for taking a small sample, maybe 10 or 100 or 1,000 or whatever students, poll them and see what proportion of those folks text during class. So again, our notation for the true population proportion is P. Okay, and to estimate it, we use this guy. Remember, P hat is how we say that. P hat. Okay, because it looks like a P, but it has a hat on it. Remember, in statistics, whenever we draw a hat over something, it sort of means that we're using this quantity to estimate the thing that is underneath. So P hat is an estimate for P. Okay, so the sample proportion, of course, would just be the number of successes, which we might denote by X, and then divide that by the sample size, N. Okay, that makes perfect sense, right? The total number of successes divided by the sample size. Well, just as was the case with random sample means, the sample proportions are random as well. That is, this thing is random, right? It depends on who you actually survey. If you survey students in my class, probably 99% of them are texting. If you survey students in another class, it may be that they take maybe that the teacher takes up the phones before class, and so none of them are texting, so 0%. Okay, so it really depends on what sample you actually get. So this is important to realize that the sample proportion P hat is actually a random variable. It has a random variable. And so you can think of it like this. Let's say you're going to do a binomial experiment where you have n trials, then P hat is just, you can think of it as the observed number of successes in your binomial experiment divided by the total number of trials. So if we could know the distribution of the sample proportion P hat, that is, if you could know the behavior of this thing, then that would help us to know how well P hat can be used to approximate P, right? We already know that maybe it makes sense to approximate the true proportion P with this sample proportion P, but how well does it actually approximate? That's what we want to know too. You should see that P hat actually behaves like a binomial random variable then divided by the sample size. Okay, so this right here is key to our unlocking the understanding of the behavior of P hat. So to help motivate our discussion now about sample proportions being used to estimate population proportions, let's go back to our fountain full of coins and let's consider drawing 20 coins at random from, say, all the pennies in the fountain. And again, we're assuming that there's an absurdly large number of coins in this fountain, just an infinite number of coins, a sea of coins, where 56% of the coins are pennies, 9% of the coins are nickels, 16% of the coins are dimes, and 19% of the coins are quarters. What's the probability of getting at least 4 dimes or at least 5 dimes? Well, to kick this off, I'm going to think about, what's my random variable here? This is really the first step. The crucial step here is to be thinking about what is your random variable. Let's let D denote the number of dimes that you observe in your sample of 20 coins. Okay, and so what I want to know is what's the probability of getting at least 4 dimes. So again, so D is the number of dimes in my 20 coin sample. So maybe I'll put out here in parentheses just to remind myself that N equals 20. What I want to know is what's the chance that D is at least 4. So that's, there are several ways I could do that. Probably the easiest way is to start off with the rule for complements and do 1 minus the probability that D is less or equal to 3. And then, this would be 1 minus. Now, what's the chance that D is less or equal to 3? It's the sum, or say K goes from 0 up to 3 of, let's see, 20 is our sample size. 20, choose K times, see, what is the probability of choosing a dime in the first place? 16%. So put in 0.16 raised to the k times 1 minus 0.16 raised to the 20 minus k. Okay? K. All right. But of course, we can use our technology built into the calculator to do this real quick, and it would just be 1 minus binom CDF. N is 20. P is the chance of success. I'm going to say it's a success if we observe a dime. And then up to and including 3. And when I do that with my calculator, let's see, go to the distribution menu and arrow down to binom CDF, 20 trials, 16% chance of getting a dime, up to and including 3. And remember, I'm using binom CDF, C here for cumulative, so that we add up all the probabilities from 0, the chance that you see 0 dimes, plus the chance that you see 1 dime, plus the chance that you see exactly 2, or exactly 3, or exactly 4. Okay, and so I do that, and of course I forgot to do my 1 minus, so I'll do 1 minus all that stuff. It's 0.401004 approximately. I'll round down there. 0.401004. What's the probability that D is at least 5? That's the next question, right? The chance that you see at least 5. There are a couple ways I could do that. One would just be to take probability that D is at least 4 and subtract off the probability that D equals 4. Right, so let's try it that way. I already have this one right here. This is this probability, so that's 0.401004 minus, let's see, the chance that D is exactly 4 is 20 choose 4 times 16% raised to the 4th power times 1 minus 0.16, 20 minus 4, like so. And so if I pull out my calculator, that's going to be, take this last entry here, subtract 20, go to the math menu, choose NCR 4 times 0.16 raised to the 4th times 1 minus 0.16 raised to the 20 minus 4, which is 16. I get 0.205911 approximately. Or, of course, I could just do 1 minus binom CDF, N, P, and up to and including 4, right? And see what that brings me. 1 minus binom CDF, 20, 16%, 4, and you get exactly the same thing. They're not exactly the same because remember we rounded in there when we found this chance that D was greater than or equal to 4. We rounded there at the 6th decimal place, so it should be off somewhere down there around the 6th or 7th decimal place, and it is. Okay, but that's okay. It doesn't make a huge difference. So same. Okay. How should you choose to do this? Well, I certainly recommend using your calculator as much as possible, but I do want to point out that there are always multiple ways to solve these probability problems, and I encourage you to think about what is the expected number of dimes, if you draw 20. Okay, let me make some room here, and again, I'm assuming that taking the sample of size 20, so this is asking for the expected value of D. Another way to write it, just symbolically, is just like that, right? Mu D. It's just N times P because D is a binomial random variable, right? So N is 20 and my success probability is 16%. So 16% of 20 is 3.2. 3.2 dimes. So we would expect, that is sort of on the average, to have to observe 3.2 dimes in a sample of 20 coins. Do not round this number. Do not round this number. Hey, should you round this number? The answer is no. I'll see this on a lot of exams. This equals 3. Okay? No, 3.2 does not equal 3, and the expected value is not 3. This is the answer. Now, would you ever expect to see exactly 3.2 dimes when you take a sample of 20 coins? Absolutely not. You would never truly, in the everyday sense of the word, expect to see that. However, on the average is what this means. On the average, this word expectation, which is what the E is for, this has a different meaning, remember. It just means, here within the context of the subject of probability, It means that on the average, we expect to see 3.2 dimes in a sample of 20. So coins. So if you were to take multiple samples of 20, sometimes you'd see 3, sometimes you'd see exactly 2, sometimes you'd see 4, sometimes you'd see 5. But if you averaged all of those counts, you would get 3.2. What is the standard deviation of the number of dimes? Okay, again, so this is easy to work out because d is a binomial random variable. So the standard deviation of d, if you remember, the formula is just the square root of n times p times 1 minus p. Okay, so that's going to be the square root of 20 times 0.16 times 1 minus 0.16, and I'll pull out my calculator for that. Get the square root of 20 times 0.16 times 1 minus 0.16 to get 1.63951 approximately. I've rounded there a little bit. Now, what's the distribution of the random number of dimes? Oh, okay. Well, we already know that. We've been using the fact that it's got a binomial distribution. Let me just write it down here. So D has a binomial distribution with n equals 20 trials and success probability P equal to 0.16. So what I'll do now is I'll use Manytab to create a picture of this distribution and go in here to the graph menu, probability distribution plot, and I want to make one from a binomial. I just want to check out a picture of this thing. Binomial, number of trials, 20 trials, event probability is 16%. Yep, okay, that looks pretty nice. Now, notice that this plot only has binomial random variable values for 0, 1, 2, 3, 4, all the way up to 9 or 10. But I know that I'm doing 20 trials. What's the chance, though, that I see, say, 10 or more successes in this case? Chance that I see 10 or more is the chance that is 1 minus the chance that I see 9 or less, which is 1 minus binom CDF, 20 trials, 16% success probability. Put a 9 in there. This number is going to be extremely small. 4 parts in, say, 10,000, okay? It's extremely small. The chance that you see 10 or more is extremely small. So, in fact, probably my guess is Manytab is actually creating this plot using a simulation program. And, in fact, when they simulated it, it looks like they didn't even get any values that were at 10 or more. Or maybe it just puts the graph window around the largest 99.99999% of the picture there. So let me make an arguably better representation of this. We'll go from 0 up to 20. In fact, maybe we'll go from -1 up to 21 so that we can see the entire picture there. What you see there is essentially that even though there is a small chance that you could see something out here at 10 or 15 or 18 or 20, it's extremely small, and so that's why the curve drops down like that. Notice that this curve is indeed it's centered right around 3.2, which is where the mean is. The shape of this curve is slightly right skewed, and that I would sort of expect that because the mean is down here close to 0. It's at about 3.2. But aside from this slight right skewness, it does look, in fact, like the distribution is sort of mound-shaped. Almost normal, in fact, except that we know that binomials are discrete random variables. Let's keep that in mind. I'll put that back over here. Now, what's the probability that the sample proportion of dimes is at least 1/5 or at least 1/4? That is, I want to know what's the probability that my sample proportion of dimes is at least 1/5. Well, guess what? I can write this inequality in here is, what if I were to multiply both sides of that inequality by my sample size? Then I just get this, right? And my sample size is 20. And what is this quantity here? Remember, p hat is the number of successes over the sample size. Multiply that by the sample size, and I just get the number of successes. The random number of successes, we've already got a symbol for that. That's d. So this is the probability that d is at least, what is n times 1/5 there? That's n is 20 times 1/5. 1/5 of 20 is 4. This is the probability that d is at least 4. We've already worked that out. I already know that that's equal to 0.401004. So this tells me that when I'm dealing with binomial experiments, I can talk about probability statements around the binomial random variable itself, which is the counts of successes, or I can also make probability statements about the sample proportions. I can phrase those probability statements about sample proportions in terms of probability statements about the binomial random variables, or vice versa. Similarly, I could calculate the probability that the sample proportion is at least a quarter. If I multiply through on that in here in the inequality again by n, I get n times p hat. That's greater than or equal to n times a quarter, which is, again, p hat here, remember, is the number of successes that you observe divided by the sample size, and then this is times the sample size right there. So all of this is just the number of successes, which is d. So it's the probability that d is greater than or equal to 20 times a quarter, which is 5, right? So it's the chance that d is at least 5, which again, we already computed that as well. So that came out to be 0.2059108 or so. What's the expected value of the sample proportion p hat and the standard deviation of the sample proportion p hat? The expected value of the sample proportion p hat. If I just replace p hat there with, what is it? It's the number of successes, the random number of successes divided by n. This is essentially, remember this E operator thing here. It just says, hey, let's average all the possible values. Let's take a weighted average of all this stuff. And if you remember that, when you take an average, if you multiply every term in the summation by a constant there, I can actually pull this out. This is 1 over n times the expected value of d, which is 1 over n times np, and lo and behold, look at that, the n's cancel and you just get p. That is, on the average, p hat is p. And in fact, as we'll see in a minute, proportions are means. So it should come as no surprise that while on the average, we already knew that on the average x bar, that is the expected value of x bar, the sample mean, is mu, because proportions are means too, then the expected value of the sample proportion should also be the population proportion. Again, more on that in a minute. But similarly then, what if I want to find the standard deviation of p hat? I'm not sure I really know how to do that, but let's think about this. What if I were to find the standard deviation of the random sample mean? I know that is sigma over the square root of n, right? It's the population standard deviation divided by the square root of the sample size. Now, if I buy into this notion that, in fact, sample proportions are sample means and that population proportions are also considered to be population means, then maybe I can solve this problem. And in fact, that is true, because notice that a proportion is just an average of ones and zeros. If you label someone with a 1 if they're a success and a 0 if they're a failure, then the sample proportion is just the sum of the ones and zeros divided by the total number in the group. So here I'm just going to square root of n down there. And what's the standard deviation for a binomial? If I'm doing one trial, it's 1 times p times 1 minus p. So yeah, so all of this is just it's just the square root. Remember, a fraction of square roots is just it's just the square root of the fraction. So it's p times 1 minus p over n, like so. So in fact, I know how to get this. It's going to be the square root of 0.16 times 1 minus 0.16 over 20. If I do that with my calculator, the square root of 0.16 times 1 minus 0.16 over 20, I get 0.0819756. So there's the standard deviation of p hat, and there is p hat. So I'm going to use Minitab to do this. I'm going to keep my distribution plot, my binomial distribution plot over here, and over here, maybe I'll do this with a simulation. I'm going to calculate some random data from, let's say, a binomial, okay? And we'll do this, say, 1,000,000 times, because whenever you want to track the behavior of something, you look at it a bunch of times, put those in column 1. We got 20 trials, and the success probability is 0.16, and there we go. So these are binomial random variables. We can think of them, this is our D, right? This is a simulation of our D variable, and over here, I'm going to say, let's let column 2 equal column 1 divided by 20. Okay, that'll give us our sample proportions, right? Because 4 is 20% of 20. 1 is 5% of 20. 2 is 10% of 20. 3 is 15% of 20, and so on. So now, if I make a histogram of the stuff in column 2, that'll just be a histogram of my sample proportions. Now let's put this on a scale from, say, negative 0.05 up to, say, 1.05. And now let's compare this with our other plot. So this first plot is the plot for the random number of dimes, our binomial experiment there. And this second plot is a histogram of sample proportions. These look the same to me, except what? Except, well, these bars are skinnier. I'm not sure if that matters. And the other thing is that the scaling down here on the horizontal axis is different. And also up here I've got frequencies, and these are probabilities. Now remember, I did 1 million trials up here. So if I take 250,000, divide that by a million, that's a quarter, or 25%. Okay, so if you rescale these the vertical axis by dividing by a million, I get exactly these numbers. Also, note that down here, these are sample proportions. All these values down here are exactly the values over here, just divided by 20, right? So if I take 20 divided by 20, then I get 1, which is way over here. These plots are essentially the same, except for the scaling. And that's exactly what I want you to see. You can talk about, if you're going to do a binomial experiment where you have exactly n trials, you can talk about, the number of successes that you observed, or the proportion of the n trials that result in success. If you can answer one of those questions, you can answer the other. So here's what I was talking about just a moment ago. Proportions are in fact means, and it's important for us to see this, because if we can realize that indeed proportions really are means, then everything that we can say about means we can say about proportions too. So for example, in a survey of 150 ice cream lovers, 57 of them favored chocolate over vanilla. So of course the sample proportion can be written as 57 over 150, and that comes out to be 0.38. Okay, 38%. Okay, 58 successes out of 150. 57 successes. 57 people favored chocolate over vanilla. You can view this as going into this as a binomial experiment where your sample size is, or your number of trials there is 150, and is 150. And the number of so-called successes that you actually observe there is 57. Then your sample proportion is 57 divided by 150, okay, which is 38%. What you don't know about here, though, is the true proportion of chocolate lovers over all ice cream lovers. Maybe that's something you'd like to estimate. So you could use this to estimate the true value of p. But at any rate, another way to view this sample proportion calculation is that it is indeed an average of ones and zeros. Here, maybe you could assign a 1 to everyone who votes for chocolate and a 0 to everyone who votes for vanilla. In that case, you'd have 57 ones and 93 zeros. So if I add up all these ones and zeros, all the 57 ones and the 93 zeros, then divide by 150, look at that. That's just an average of all the ones and zeros. This whole thing is just an average of ones and zeros. It comes out to be 57 over 150, or 38%. So indeed, proportions are averages. They're just averages of ones and zeros. So because proportions really are means, they're just special kinds of means, then what that means is we can write the mean of the sample proportion is the population proportion. Just like we had the mean of the sample mean was equal to the true population mean. Also, because this guy, remember, all this stuff is the standard deviation for one trial of a binomial experiment with success probability p, then remember this is how you get the standard deviation for the random sample mean. Well, then I just take this and stick it in there for sigma, and it appears here, and then voila, this is my formula for the standard deviation of the random sample proportion, also called the standard error. Note, as was the case when you were talking about the standard error for random sample means, the larger the sample size, the smaller the standard error is when you estimate the true proportion with the sample proportion. We like that. We like that. In fact, we've known this since we were kids, and that is that generally if you take a larger sample size, your estimate is going to be better. Better in what sense? Well, better in this sense. The larger your sample size, the smaller your standard error is, or the smaller the standard deviation is of your estimate. Your estimate is going to tend to hit closer and closer and closer in to where it's supposed to be.